Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about the electric potential due to a continuous charge distribution. So to that end we need to recall what an electric potential is. So the electric potential is V is defined as potential energy U per unit charge. Probably, if we want to be really formal here, it's the electric potential energy per unit charge. So V is defined as U sub E over Q. Second thing to note is that it is a scalar quantity. So yay, it's not a vector quantity like the electric field. And then the third thing is what is the potential due to an individual point charge or a discrete point charge. The potential due to a point charge, we'll call it capital Q, is Coulomb's constant times Q over R, or in other words 1 over 4 pi times the permittivity constant epsilon naught, all times Q over R. And reminder, these two constants, K sub C and epsilon naught, have set universal value. So Coulomb's constant is about 8.99 times 10 to the 9 Newton meters squared per Coulomb squared, whereas the permittivity free space epsilon naught is 8.854 times 10 to the negative 12 Coulomb squared per Newton meter squared. That's basically the backdrop. I suppose we could add to all this that potentials add. So this is simple scalar addition. So if I want to get a total potential at some point, I basically can just add V1 plus V2 plus V3, etc. Or in other words, if I want from a bunch of point sources the total, then I basically have the Coulomb's constant, or 1 over 4 pi epsilon naught, times basically the first charge divided by the first distance, plus the second charge divided by the second distance, plus the third charge divided by the third distance, etc. And again, these are scalars, so they are much easier to add than, say, electric fields, which are vector quantities. So all of that is dealing with individual point charges, which is a good starting point. But what if you have a distribution of charges? So what if you have some object like this and you want to know what is the total potential at some point out here due to this distribution of charge? Well, this distribution of charge is going to have individual elements dq, which are still some distance r away. And so if I want to get the total potential here due to all of those, remember that integration is kind of akin to summation, but for very small elements being added. So you could basically do K sub C times dq, differential element charge dq, over r, or if you prefer 1 over 4 pi times epsilon naught integral of dq over r. I've pulled the constants out over here, I left the constant in over here, but otherwise this is the basic approach either way. Now, as with many of the other integrals that we've done, for example, all the integrals that I did in finding E fields and forces due to E fields and so on, the tricky thing here is not figuring out what should this equation be. This equation just is what it is. You know, you could put a box on this equation and say, yeah, this is a base equation of sorts. So in some ways it's like, hey, we're done. But it gets a little more complicated in as much as that the dq here, the differential element of charge, may be a function of distance r. It may be that both of these things are a function of some other variable, and so casting everything into a common set of variables is kind of the hard part. As an example, let's consider a semi-hollowed sphere. Okay, so semi-hollowed sphere basically means that we're looking at a sphere that is made more or less of solid material, but it's been hollowed out partially. So it's been hollowed out in such a way that the inner radius is r1 and the outer radius is r2, and there's a total charge of q which is uniformly distributed through this sphere. So this is a non-conducting sphere, in other words, but it's got a uniform charge distribution. So now we ask, all right, what would the potential be at this position here in the middle? And to do that, we can basically use the same equation that I wrote out up here, v total 1 over 4 pi epsilon naught integral dq over r. So at this location, v is going to look like 1 over 4 pi epsilon naught integral, and we're really integrating against r in some way. So we could say dq over r, and what we expect is that dq needs to be converted to some function of r times dr. Okay, so how might we go about doing that? Well, you know that we can take some volume element of this sphere, and this volume element has in it a charge dq. And if it has a uniform charge distribution, we could call that distribution, we could say it has a density of rho, such that rho is defined by q over total volume, which basically is q divided by 4/3 pi times the outer radius squared minus the inner radius squared. All right, so if that is the case, then we could say something along the lines of dq is equal to rho times dv. Okay, so that right there is where our sort of radius is going to come into play, because our volume element dv could be cast as a dx, dy, dz, but it can also be cast in terms of a radius, specifically a radius squared times the sine of theta times dr d phi d theta. So these are equivalent volume elements. What that's going to allow me to do is basically my dq is now rho dv is now rho times r squared sine theta dr d theta d phi divided by r. Okay, so my potential has now become a triple integral. So I got 1 over 4 pi epsilon naught integral, and this could be my radius integral, and that's actually going from r1 out to r2. Integral, this is actually going from theta equals 0 to pi, and integral, and this is going from phi is equal to 0 to 2 pi. So this is my total volume integral. And then what I have basically as my integrand, dq over r becomes r squared sine of theta dr d theta d phi, all divided by r. Okay, good news, I can sort of cancel some r's here, and I'm just left with an r sine theta dr d theta d phi. So now what I have to do is kind of come down here and sort of integrate piecewise. And so this right here is integral number 1. And so integral number 1 in all of this is just d phi integrated from phi equals 0 to 2 pi. And so that's just phi evaluated from phi equals 0 to 2 pi. And so that part just gives me a 2 pi. Okay, next one out is basically this part of the integral. And this part of the integral has a sine theta and a d theta in it. So I can kind of pull the 2 pi out front, and I can kind of like rewrite my integral now to say 2 pi divided by 4 pi times epsilon naught integral on r. So that's r1 to r2. And then if I sort of pull the r parts out, I have r, then I have what's left in here, and then I have a dr. This 2 pi term came out of that first integral. Okay, so second integral is integral from theta equals 0 to pi of sine theta d theta. Well, that's straightforward. You know that that integral is going to give you negative cosine of theta evaluated from theta equals 0 to pi. And so that is negative cosine pi minus negative cosine 0. Cosine of 0 is 1. Cosine of pi is negative 1. So I have minus negative 1, so that's positive 1, minus negative 1, so that's plus 1 more, so that's 2. So now my potential is, if I include the 2 times the 2 pi, essentially I now have 4 pi divided by 4 pi epsilon naught. I guess I could just cancel the 4 pi's here. And then I have an integral from little r equals big R1 to big R2 of r dr. That one's also easy. So now I have 1 over epsilon naught. Integral of r dr is 1/2 of r squared, evaluated from r1 to r2. And so this ends up being 1 over 2 epsilon naught times r2 squared minus r1 squared. Now, important thing here, I kind of forgot a piece of my integrand. This was supposed to be a dq, so I needed to have a rho in front of all this. That rho is a constant, so it can just kind of be pulled out. So that's a very quick and easy fix. At this point, I can say we're almost done. In some sense, this right here is pretty good. The thing is, the original problem didn't give us stuff in terms of a rho. It gave us stuff in terms of a q. So remember that rho is actually total charge q divided by total volume, which is 4/3 pi times r outer cubed minus r inner cubed. That basically just matches what we did on this page, although on this page I accidentally wrote squared instead of cubed. They are in fact cubed, these are volumes. So if you come back here and look at the voltage, I've said rho over 2 epsilon naught. So my voltage is rho over 2 epsilon naught, and then times this difference of squares, r2 squared minus r. So to finish this out, what has to happen is we need to sort of like substitute all of this in where we see a row. What we're going to get when we do that is that our potential, our electric potential value is Q divided by 4/3 pi times R2 cubed minus R1 cubed, and that is the rho value, all times R2 squared minus R1 squared, and then that divided by 2 epsilon naught. Now you may look at this and think, hey, can that cancel? I mean, can I just divide out an R2 squared and an R1 squared from these two terms respectively? Unfortunately, the answer to that is no, not directly, because you have to be able to divide R2 out of both terms, not out of one or the other. And the simplification that is allowed comes from the fact that there are basic algebraic formulas for sum of cubes, difference of cubes, and for that matter, difference of squares. The sum of cubes formula, basically what you do is you, for a cubed plus b cubed, you're going to have a plus b times a squared minus ab plus b squared. For the difference of cubes, that is a cubed minus b cubed, what you're going to get is a minus b times a squared plus ab plus b squared. And for the difference of squares, you have a squared minus b squared is just a plus b times a minus b. What that means is that this form that we have here does in fact reduce slightly. So we can write this as basically Q, or 3Q, actually if we move the 3 up here, times R2 cubed minus R1 cubed, times R2 squared minus R1 squared, divided by, and then we have 4 times 2, so that's 8 pi epsilon naught R2 cubed minus R1 cubed. Now it's this sum and difference of squares that we're interested in. So we've got 3q divided by 8 pi epsilon naught times, and then the numerator becomes R2 plus R1 times R2 minus R1. And the denominator becomes R2 minus R1, it's the difference of cubes, times R2 squared plus R1 R2 plus R1 squared. So we're basically making use of a difference of cubes, this form, and a difference of squares, this form. And when we do that, we see that we have an R2 minus R1 both on top and on bottom. So if we wanted to simplify this equation further, what we end up is 3q over 8 pi epsilon naught times R2 plus R1 divided by R2 squared plus R1 R2 plus R1 squared. And this does not further simplify. The bottom is not the square of the top because you would need an additional factor of 2 in this middle term to make that happen. So this right here is sort of your final answer for what is the charge, or what is the potential at the center of that charged, partially hollowed sphere. So that is all for today's video. We have learned, hopefully, the basics of how to do potential due to a uniform, or really due to a continuous charge distribution. It need not be a uniform one, but my example happened to be a uniform charge distribution. So hopefully you found this example helpful. It is, as far as I know, not an example that I pulled out of any particular textbook, so you should be able to read whatever, go read your textbook and you should have some other examples. And so hopefully between all that, you'll kind of get this skill down. Hopefully you found it helpful. As always, thanks for watching.